Hi there, welcome to this Engineering Maths 2 Outcome 2 lecture. In this lecture we're going to look at second derivatives and their associated properties. So the second derivative is what happens when you differentiate a function twice. So the symbols that we use d2y by dx squared, that's how we say this, or f double dash of x. The number of dashes tell you how many times you differentiate, or also y double dash is acceptable as well. Just depends on the variables being used. We can also use this rule to then find further derivatives. So, for example, the third derivative, fourth derivative, etc. They tend to appear less frequently. The second derivative is very useful, though. Okay. So, to find the second derivative of something, we'll take this example, and all we're going to do is we're going to differentiate, and then we're going to differentiate again. So, y equals x squared plus sine x minus e to the minus 2x. So our first derivative, which we will call dy by dx, is going to be, so x squared becomes 2x, sine x becomes plus cos x, and then you bring the minus 2 down and multiply, so that's going to become plus 2 e to the minus 2x. So that there is in red is your first derivative. Okay. Our second derivative, which I'll do in blue, the way we write that is d2y by dx squared. So we just differentiate our first derivative. So differentiate 2x becomes 2. Differentiate cos x, that becomes minus sine x. And differentiate plus 2e to the minus 2x. So bring the minus 2 down, times it by the 2, so that's going to become minus 4e to the minus 2x. So that, in blue, is our second derivative. Okay, that should be straightforward. So all we're doing is we're just differentiating the number of times we need to. So let's find the third derivative of this. Like I say, third derivative probably less likely to come up. Okay, it does have applications, but they're quite infrequently used. So first derivative, so dy by dx. So bring the 4 down in front of the 5 and times it, so that's going to be 20x to the 3. And then plus cos of 2x is going to become minus, because cos becomes minus sine, and then bring the 2 out, so minus 2 sine 2x. Okay, so that's your first derivative there in red. Second derivative, again, we'll do in blue. So d2y by dx squared. Okay, differentiate this term. So we're going to bring 3 down and multiply by the 20. So it's going to be 60x squared. And then sine becomes cos. Bring the 2 out and multiply. So that's now minus 4 cos of 2x. So that would be your second derivative. And then if you were asked to find the third, we'll do in purple. So the way that we say that is d3y by dx cubed. So I'll bring the 2 down and multiply, so that's going to be 120x. And then cos becomes negative sine, so that's going to become positive there, because we're going to get 2 negatives. Bring the 2 out and multiply, so it becomes 8 sine of 2x. So that would be our third derivative there in purple. Okay. All we're doing is differentiating the appropriate number of times. Now, let's look at where this might be useful. So one application of differentiation is to find the turning point of a function. So you can see the different types of turning point below. So in this first one, we've got a maximum turning point. You can see, imagine this is like a hill. We can see that the maximum turning point is at the top of the hill. You go up, and then at some point you start coming down. So that is your turning point up here. Similarly, a minimum turning point, like a valley, we go down the valley and then we start coming back up again. So there's a turning point at the bottom. Now you can actually have a turning point where you're going uphill and then you go flat for a bit and then you start going uphill again, or vice versa with downhill. This is called a point of inflection. So we actually briefly have a turning point here and here. Okay, imagine if you're driving a car and you're coming around the bend and then immediately you go straight and then you start going around another bend. Okay, So at some point the steering will be completely straight. So what we can do is we can find the turning point by setting the derivative of the function equal to 0. Okay, this is because at the turning point the gradient is 0. So look at this function here. This represents approximately x squared minus 2x plus 1. So at this point at the bottom, that's your turning point, and we can see that the gradient there is flat, very briefly. Okay, at the bottom of the hill, it's flat. Therefore, the gradient is equal to 0. And we know that the gradient, another way of describing that, is the first derivative. So dy by dx is equal to 0. So what we're going to do to find the actual value of a turning point is we're going to differentiate, and then we're going to set that equal to 0 and solve it. So find the turning point of the function x squared minus 2x plus 1. So what we do first is we differentiate this function. So x squared becomes 2x, minus 2x becomes minus 2, and plus 1 becomes 0. Okay, so we've differentiated that. This is our first derivative. Now what we need to do is we now set this equal to 0. So we'd say that dy by dx equals 0. That means that 2x minus 2 is going to be 0. Okay, and now we can solve that to find the value of what x is going to be for that turning point. So we bring the 2 across and add it. So that will be 2x is equal to 2. And then finally divide by 2. So that means that x is equal to 1. So that is the x value of the turning point. Okay, now the turning point, we would have two coordinates. We would have an x coordinate and a y coordinate. What we can now do to find the y coordinate is we can take that point and we can sub it into the original equation. So as x equals 1, y is equal to 1 squared minus 2 times 1 plus 1. And that will just give me a total of 1 minus 2 plus 1 is 0. Okay, so we've therefore got out the coordinates of our turning point. So we can say there is a turning point at 1, 0. Okay. So we've seen there's different types of turning point in a couple of slides ago. So let's look at the gradients of these for a moment. Now we can see on this one here that this is a minimum turning point. You can see that's at the bottom. Okay, so this is a minimum turning point. So we know at the bottom, this bit here, we know that the gradient is equal to 0. But if we look at the left-hand side of this, we can see that we're going downhill. So therefore, all the gradients before this point are negative gradients. Whereas on this bit, we're going uphill. So therefore, all the gradients on this side of the turning point are positive gradients. Okay, so a minimum turning point goes from negative to positive. Okay, because it will go negative, become 0 very briefly, and then become positive. Let's look at a maximum turning point. So this is if you're walking at the walking up a hill, and you reach the top, and then you start coming down again. Okay, so we know here, top of the hill, very briefly, it's flat, so that's got a gradient of 0. Now we're going up the hill, so all these gradients are positive from left to right, and then on this side, they're going downhill. So therefore, all these gradients must be negative. So a maximum turning point goes from positive to negative. Now, points of inflection are a little bit interesting because if you imagine here, this is your gradient of 0, very briefly. Well, before that, we've got positive gradients. And then after that, we've also got positive gradients. In this one at the bottom, very briefly, it's 0. But then either side of this, we've got negative gradients. So negative, 0, and then negative. So these are both called points of inflection. So this is called a rising point of inflection, and this is called a falling point of inflection. Okay. Now, it's useful to know how the function is changing. So what we say is we need to find the nature of a turning point. And what that means is it a maximum, a minimum, or a point of inflection? Okay. So what we can do is we can use a nature table to test a point either side of the turning point. And then we compare the gradients. So this is the question we've just done. Y equals x squared minus 2x plus 1. And we know from previously that dy by dx is equal to 2x minus 2. We also know that the turning point is at 1, 0. Remember, that's your x coordinate, that's your y coordinate. Now, we're really just interested in the x coordinate, okay? So what I'm going to do is I'm going to set the x coordinate in the middle of my nature table here, and I'm going to pick a point either side of 1. So I'm going to choose 0 and 2. Okay. And what I'm going to do is I'm going to put these numbers into my first derivative, and that will tell me the gradients at each of these values. So if I substitute 0 into 2x minus 2, the derivative, then that's going to be 2 times 2 minus 2, sorry, 2 times 0 minus 2, which is going to be negative 2. When I sub 1 into there, well, I know that that is my turning point, so that's going to be 0. 2 times 1 minus 2 is 0. And then when I put 2 into there, 2 times 2 minus 2 is equal to 2. So what I've got is I've got a negative gradient, which is going downhill. So that's negative, so it's going downhill. I've got a 0 gradient, which is flat. And then I've got a positive gradient of 2. So that's going uphill. So we can see by the shape this makes that it must be making a curve that's going downhill, then flat, and then back uphill. So we can see from there that therefore that must be a minimum turning point. So we can say that 1, 0 is a minimum turning point. Okay, just by comparing the gradient either side of your turning point. Okay, we can see how it changes. So in this case, go from negative to positive. So we can just sketch that shape. Okay, so it makes that, so it must be minimum. Okay. Okay, so the other way we can work out the nature of a turning point is using something called the second derivative method. Okay, so at the turning point we can use these rules. So if d2y by dx squared is less than 0, i.e. if it's negative, then the turning point is a maximum. If d2y by dx squared is greater than 0, i.e. positive, the turning point is a minimum. Okay, and if the second derivative is equal to 0, unfortunately we need to go back to the table of signs to determine the nature of that point. Okay, sometimes that gives a point of inflection, sometimes it doesn't. Okay, now these can be a little confusing because you would think, well, a negative number should be a minimum and a positive number should be a maximum, but actually it's the other way around. So you've just got to remember that the converse is true. Okay, so if the second derivative is negative, then it's a maximum. If the second derivative is positive, then it's a minimum. Okay, so let's look at an example like that. So using the second derivative method, find the nature of the turning point for the equation y equals 2x squared minus 12x plus 1. Now, because it says use the second derivative method, you must use the second derivative method. If it doesn't say that, if it just says find the nature, you can use either a nature table or you can use the second derivative method. Okay, so the first thing we need to do is we need to differentiate. So dy by dx is equal to 2x squared becomes 4x, and minus 12x becomes minus 12, plus 1 becomes 0. Now remember, this is what we now need to set equal to 0. So we've got a turning point when dy by dx is equal to 0. So let's just put 4x minus 12 equal to 0. And then we need to solve that. So bring the 12 across and add it. And then divide by 4. So x must be equal to 3. Okie dokie. Now at that point we can find the y value. So we just sub 3 into there, and that will find the y value of that. So at x equals 3, y is going to be 2 times 3 squared minus 12 times 3 plus 1. So it's going to be 9 times 2 is 18 minus 36 plus 1. So it's going to be minus 18 plus 1, so negative 17. Okay, so that's the value of the turning point, 3 minus 17. Right, we're now going to use the second derivative method. So we differentiate again. So 4x minus 12. Well, 4x just becomes 4, and minus 12 just disappears. So we've got a second derivative of 4. Now, we just need to know if that's positive or negative. The actual number itself is not important right now. So we know that d2y by dx squared is positive, it's greater than 0. So therefore, that means that 3 minus 17 is a minimum turning point, because this is positive, it's therefore a minimum. You can see that back on the previous slide. So that's how we use a second derivative to find the nature of the turning point. And the nature is either the maximum, the minimum, or a point of inflection. Okay, thanks for watching. There'll now be some work to do.